This lecture is on articulations. What are articulations? Articulations are unions of two or more bones. The ends of bones are shaped so that they fit together. Less stable joints are more movable because the bones fit loosely. More stable joints are less movable because the bones fit tightly. Joints are classified based on structure and function. There are three structural classifications of joints: fibrous joints, cartilaginous joints, and synovial joints. Fibrous joints contain a fibrous membrane. Examples are gomphoses and sutures. Cartilaginous joints contain fibrocartilage. Examples are intervertebral discs and pubic symphysis. Synovial joints contain a cavity filled with thick synovial fluid. Examples are all freely movable joints. This illustration shows the fibrous joints: gomphoses in the teeth, holding your teeth in place in the skull, and the sutures, holding the cranial and facial bones together. The cartilaginous joints include the intervertebral discs and the pubic symphysis. They resist compression in weight-bearing areas. The synovial joint contains a joint cavity filled with synovial fluid. This is found in all freely movable joints. There are three functional classifications of joints: synarthroses, amphiarthroses, and diarthroses. Synarthroses are immovable, and examples are the fibrous joints. Those were the gomphoses and the sutures. Amphiarthroses are slightly movable. Those are the cartilaginous joints, such as the intervertebral discs and the pubic symphysis. Diarthroses are freely movable, and this is all synovial joints. Arthroses means joint or articulation. Syn means together. Amphi means between. And diarthrosis is freely movable. Dia is thorough or complete. So no movement for synarthrosis. They're fused together basically. Slight movement, so they're between none and freely. And then dia is thorough movement. This illustration summarizes what we just talked about. We have limited mobility up in red here, down to freely movable in blue. Remember, the more movable a joint, the less stable it is. So we sacrifice stability for mobility, which is very important though, because we have to move in our environment. The body has ways to stabilize freely movable joints, and we'll discuss that later. But freely movable joints are more likely to become dislocated or injured than are immovable joints. So the fibrous joints are the synarthrosis or immovable joints. Cartilaginous joints are going to be slightly movable, and then synovial joints are freely movable. Let's talk about synovial joints. The synovial joint is the main focus of this chapter. There are 6 main structures of synovial joints. The articular capsule, which surrounds the entire joint, is made of a fibrous layer of dense irregular connective tissue. The synovial membrane secretes synovial fluid. The articular cartilage reduces friction between articulating bones and is composed of hyaline cartilage. The joint cavity is a potential space. Synovial fluid is secreted by the synovial membrane into the joint cavity. Synovial fluid is an oily, viscous fluid that provides lubrication, shock absorption, and nourishment to the joint. It contains glucosamine, chondroitin, and hyaluronic acid, along with other proteins. If you take those supplements, you are taking them to strengthen the integrity of the synovial fluid and keep the joints freely movable. Ligaments connect bones together. and they are composed of dense, regular connective tissue. This is the illustration of the 6 major features of synovial joint. The joint capsule is a fibrous membrane that surrounds the entire joint. The synovial membrane secretes the synovial fluid. The articular cartilage covers the ends of the long bones. The cavity is the space between the 2 bones. Notice that the bones don't actually touch. And the synovial fluid fills the space, keeping the joints lubricated. And the ligaments bind the joints together, helping to stabilize them, yet allowing for the proper amount of mobility. Accessory structures are found amongst most synovial joints. And they include bursa, tendon sheaths, and fat pads. Bursa are fibrous sacs that contain synovial fluid. They reduce friction between adjacent structures during joint activity. Tendon sheaths are elongated bursa that surround muscle tendons. They are common where several tendons are crowded together within narrow canals or spaces. Fat pads act as a packing material and provide protection. The bursa is a fibrous sheet filled with synovial fluid. It acts as a ball bearing. The tendon sheath is an elongated bursa that surrounds the tendons in narrow spaces. Here's that movement of the ball bearing. It kind of rolls with the tendon or ligament and the articular cartilage here of the joint so that it reduces the friction between the tendon or ligament and the bone. Some synovial joints have a meniscus. A meniscus is a large, C-shaped fibrocartilage located in a few synovial joints, such as the knee. It provides shock absorption and extra stability. Fibrocartilage is very good at resisting compression. It's like the rubber in a tire. Synovial joints rely on the following for stability: articular surfaces, ligaments, and muscle tone. Articular surfaces are shapes formed by the bones themselves. An example is where the humerus articulates with the ulna to make the elbow joint. The humerus is rounded and the elbow joint has a notch. Ligaments prevent undesirable movements. Intrinsic ligaments are associated with the articular capsule. Extrinsic ligaments are outside of the capsule. So it's basically like the joint's own ace bandage that will wrap around and help to limit mobility, yet still provide enough to perform the necessary movements. Muscle tone is the continuous pull of muscles on the tendons and the bones. This is actually the most important stabilizing factor. Let's look at some movements of synovial joints. Movement occurs when muscles contract. Muscles put tension on bones, moving them when the tension is high enough to overcome the resistance. The resistance will be the weight of your bones and flesh and whatever object you are holding. Movement types are generally paired, with one being the opposite of the other. The range of motion varies across different planes. Recall we have the frontal plane, which divides the body into anterior and posterior halves. The horizontal or transverse plane, which divides the body into superior and inferior halves. The sagittal, which divides the body into right and left halves, and the oblique, which cuts at a diagonal. This illustration shows the opposite movements of the muscles on a joint. The biceps contracts and causes the forearm to flex. So this is flexing the elbow joint. And then when the triceps contracts, it will extend the elbow joint because it will put pressure to pull the ulna, straightening out the arm. The range of motion of a synovial joint can be measured by the number of planes in which they move. Non-axial joints do not move in any plane. Uniaxial joints move in one plane. Biaxial joints move in two planes. And multi-axial joints move in more than two planes. So for the non-axial joints, they do not move in any plane. And an example is the carpals. Carpals glide but do not move. They just kind of wiggle. Uniaxial joints move in one plane. For example, the elbow joint moves only in the sagittal plane. Biaxial joints will move in two planes. For example, the knuckles between your digits and your metacarpals. They move in both the sagittal and the frontal planes. So you can flex and extend your fingers, and you can also abduct and adduct, meaning you can spread your fingers apart and then pull them back together. That's a biaxial joint. Multi-axial joints move in more than two planes. We have two types of ball and socket joints, our shoulders and our hips. And these move in all four planes. You can draw a circle in space. This is called circumduction, and that is a feature of a multi-axial joint. This illustration shows the uniaxial elbow joint. So again, we're seeing flexion of the elbow and extension of the elbow. When the biceps pulls on the radius here, it will pull the radius and ulna towards the humerus, decreasing that angle. That's flexing the forearm. And then to extend the forearm, the triceps will pull on the ulna, and it will cause the ulna to straighten the arm out, and that is extending the elbow. So that's a uniaxial joint. It can do this one pair of movements in one plane. So it can do flexion and extension in the sagittal plane. That's a uniaxial joint. The biaxial joint can move in two planes. So the top is showing the flexion and extension of the knuckle joints, which is where your digits meet your metacarpals. Digits and metacarpals. So flexion will increase the extension will increase the angle of the joint, so it's straightening your fingers out. That's extension. And then flexion will decrease the angle between the joint. And then abduction and adduction of the fingers. When you are spreading the fingers, that is abduction. And then when you pull the fingers back together, that's adduction. So here we're seeing the hand in adduction, or adduction to abduction to adduction. So we're moving into planes. The flexion and the extension is happening in the sagittal plane. The abduction and adduction are happening in the frontal plane. Let me see a multi-axial joint. This is the ball and socket of the shoulder. So the head of the humerus fits into what's called the glenoid cavity of the scapula here. And it can move in all planes. So it can draw a circle in space called circumduction. So it moves in the sagittal, frontal, horizontal, and even the oblique planes. Then we see the carpals. These are our non-axial joints, and they don't move in any plane. They just kind of wiggle as you wiggle your wrist and wave. The axial part is referring to the axis of our body, because the planes, if you recall, are dividing our body into halves along that central axis. All right, 6 types of synovial joints are named for their movements. Movements will be defined in the next few slides. I went ahead and gave you a bit of a rundown of them. So let's look at those 6 types of synovial joints. Plane joints are non-axial and perform gliding movements. Examples are the carpals. Hinge joints are uniaxial and perform flexion and extension. A good example is the elbow joint. It's like opening and closing a door. Pivot joints are uniaxial and perform rotation. So basically we're pivoting or rotating along the axis of the body. So good examples are the atlas and axis when you are rotating your head in a no position. And then the radius and the humerus when you are pronating and supinating your palms. To supinate your palms are facing forward. Then to pronate them, you rotate the radius and humerus and your palm faces back. The other three types of synovial joints based on their movements are the condyloid joints, which are biaxial, and thus they perform the flexion and extension, abduction and adduction. A good example is the knuckles. The condyloid joints kind of look like they have wheels. Saddle joints are biaxial and they perform opposition. And the saddle joints look like a saddle, hence their name. Opposition is when you can touch your pollex to your pinky. And then the ball and socket joints are multi-axial, and they literally look like a ball fitting into a socket. Like you take your fist and you put it into your opposite palm. That's the ball and socket joints. Or you catch a softball or a baseball in a glove. And these can do flexion, extension, abduction, adduction, circumduction, and rotation. So they can do like a whole lot of movements. And the examples there are the shoulders and the hip joints. Here's rotational movements of the atlas and axis. Oops. So it's a pivot movement. Pivot means to rotate, basically. So we're rotating on the long axis of the body. And this is the actual joint here that's doing that. This is what's rotating. And then this is the pronation and supination of the palm. So this is the palm anterior in anatomic position. To do pronation, you rotate the palm to where it's facing behind you. And then supination rotates the palm back to anatomic position. I had a student say once that when you hold your hand out to get food, give me some supper, supination. Figure A illustrates the pivot joint between the atlas and axis. Figure B illustrates the hinge joint between the humerus and the ulna, it's your elbow. Figure C illustrates the saddle joint between the pollex and the first carpal bone, the trapezium. And this is when you can touch your finger to your pinky. D illustrates a plane joint. So we talked about them between our carpals. They're also between your tarsals. Figure E illustrates the condyloid joint. So you see it's kind of like a wheel. It's not completely round. It's more just like a wheel. And here we see this is between the radius and the carpal bones of the wrist. So this helps you to flex and extend your wrist. And I guess kind of wiggle it, abduct and adduct it. And then this is the ball and socket joint. So notice that it looks like a ball in a socket, and this is in the hip bone in this instance. And yes, the hip bone can do flexion and extension, abduction, adduction, circumduction, all kind of stuff. Alright, so now let's define all these movements formally. Movements of joints are angular, rotational, or other. Special movements, if you would. Angular movements increase or decrease angles between two bones. Flexion and extension are paired together. Flexion decreases the angle between bones, brings bones closer together. So the example that I've given you is using the elbow to bring the forearm towards your upper arm. Extension increases the angle between bones. So the example is using the elbow to take the forearm away from the upper arm. If you go above the limit of 180 degrees, you are hyper extended. And so when you hyperextend your neck to look up at the ceiling, that is hyperextension. Sometimes if you have like Ehlers-Danlos syndrome, you can actually bow your elbow out a little bit, and that is a hyperextended elbow. Some people will suffer from a hyperextended lumbar area, and that is called lordosis. Lateral flexion occurs when the trunk of the body bends laterally away from the midline. Figure A shows the flexion and extension of the neck. So when the neck is straight up and the face is looking forward, that is an extended neck. If you're looking up at the ceiling, that is hyperextended. When you bring your chin towards your chest, that is flexing the neck. Figure B shows flexion and extension of the elbow. So in elbow flexion, you're bringing the forearm towards the upper arm. And in extension, you're taking the forearm away from the upper arm. And then pointing your fingers straight forward is extension. And then pointing your fingers towards the sky is hyperextension. Figure D is showing flexion and extension of the knee. So when the leg is straight and your feet are on the ground, that's extension of the knee. And then when you bring your heel towards your hamstrings or your thigh or your butt, that is flexing the knee. So we're decreasing the angle between our foot and our thigh. And then lateral flexion. See how she's doing a lateral bend, if you would, where she's bringing her shoulder towards her legs. Some more angular movements. Dorsiflexion and plantar flexion are going to be paired. This is the flexion and extension of your ankle. So dorsiflexion occurs when the ankle joint bends so that the dorsum or superior surface of the foot moves towards the leg. So when you're pointing your toes towards the ceiling, that is dorsiflexion. So we're decreasing the angles between our foot and our shin. So that's flexion. Plantar flexion occurs when the ankle joint bends so the dorsum moves away from the leg. So example is when you point the toe towards the floor. Why they don't call that dorsal extension, I don't know. But they call it plantar flexion. So basically the bottom of your feet is moving away from your shin. This is a pretty cool movement between the tibia and the talus. More angular movements. Abduction and adduction are generally paired together. Abduction is the lateral movement of a body part away from the midline, and adduction is the medial movement of the body part toward the midline. So abduct, it's to take away. Adduct is to add it back to the body. So there's a lot of examples. So let's look at the illustrations here. This is the abduction of the arm. So she's lifting her arm laterally away from the midline of her body. We call those lateral lifts. And then adduction, she's adding her arm back towards the midline of her body. It's like drawing snow angels. This is the abduction and adduction of the wrist that I mentioned. Here's the palm in anatomical position. When you abduct, you move the palm and the thumb basically away from the midline of the body. It's kind of hard to do. And then adduction is when you move it back towards the midline of the body. So like a little bit of a wave. Your carpals are gliding in that moment when you're doing that. Here's the abduction and adduction of the hip, so the leg basically. So to abduct the leg, you're lifting at the hip here, lateral raises of the leg. Pretty good for moving your hip muscles. You've got your hip flexors in this area, so abduction and adduction are good movements for those. And adduction is when we're adding our leg back towards the midline of our body. And then here's the abduction and adduction of our digits. So to abduct the digits, you're spreading your fingers apart, and to adduct them, you're bringing them back together, adding them back to the midline. This straight line indicates the midline of the arm. Circumduction is the last angular movement, I believe, and it includes the following motions. This is the ball and socket joints of the shoulder and the hip. So this is where the ball would be, the head of the humerus here and the head of the femur. It's the proximal end of our appendage where the limb connects to the body. So it is going to remain relatively stationary. The distal end is going to be able to make a circular motion, though, from that relatively stationary movement, small movement of the ball and socket joint. So it makes this imaginary cone shape. Rotational motion occurs when a bone pivots on its own longitudinal axis. Lateral rotation and medial rotation are paired. Lateral rotation turns the anterior surface of the bone laterally, and medial rotation turns the anterior surface of the bone medially. There are 3 examples here. We have the rotation of the head, arm, and leg. Pronation and supination go together, and they include the medial rotation of the forearm, so the palm of the hand is posterior, and then the lateral rotation of the forearm, so the palm of the head is anterior. So when the hand is posterior, it is pronated. When the hand is anterior, as in anatomic position, it is supinated. Eversion and inversion are paired together. Eversion occurs only at the ankle joint, and the sole turns laterally away from the midline of the body. Inversion occurs only at the ankle joint, and the sole turns medially, bottom of your foot. Athletics will use pronation and supination interchangeably with eversion and inversion. So basically, pronation, when your palm is facing behind you, that will be the interchangeable form of eversion. Basically, it's like your sole is turned away from you. And supination, which if you remember, that's the anatomic position where your palms are facing in front, it's interchangeable with inversion. So the sole is towards the midline of the body. Just a couple other movements. Protraction and retraction go together. Protraction is the anterior gliding movement of the jaw, and retraction is the posterior gliding movement of the jaw. And then depression and elevation go together. Depression is opening the jaw or lowering the mandible, and elevation is closing the jaw or raising the mandible. We can also move our mandible side to side. That's a strictly mammal feature. Only mammals can do that. So we can chew. I believe this is the last of the movements. See how important all of these freely movable joints are? We wouldn't be able to accomplish much without them. Those of you who suffer arthritis, unfortunately, feel the effects of that. Opposition is the movement of the thumb towards the tips of the fingers. So when you can touch your thumb to your pinky, that is opposition. And then, of course, you can do all the other digits, the pointer finger or digit 2, the index or the middle finger, which is digit 3, the ring finger, which is digit 4, and then, of course, your pinky, which is digit 5. Reposition is when you go back to anatomic position. This is what enables us to grasp objects. This was hugely important in our success as humans, to be able to stand upright on 2 legs and grab things. And of course, our big old brains. Okay, let's talk about a couple of physics. Bones act as levers. A lever is an elongated, rigid object that moves on a fixed point called a fulcrum. Joints are the fulcrum. So your bone is moving. It's a rigid object that's moving along the fulcrum. So here's the fulcrum in this picture, this red triangle, and the lever is the blue bar, kind of like a seesaw. The effort is applied by muscle tension. So here's somebody applying muscle tension to the blue bar here and putting an effort to move the load. The load is the resistance, and it's the weight that has to be moved. So if effort exceeds resistance, good luck there, buddy. Moving 1 ton ain't gonna happen. So there's not gonna be any movement here. But if this was maybe like 1 pound, then of course he would have enough effort to move this. 3 types of levers are classified by the location of the effort, fulcrum, and resistance. First class levers have the fulcrum in the middle. An example is the flexing and extending the nape of the neck. It's basically flexing and extending your neck. The fulcrum is the joint between the occipital bone of your skull and your atlas. So when you're nodding your head, yes, and that is the first class lever. A second class lever has the resistance in the middle. So an example here is standing on your tiptoes. The resistance is your body, so the weight of your entire body. The fulcrum are going to be all those joints between the digits, your toes, and your metatarsals. And then the effort is your calf muscles. Third class levers are the most common type and have the effort in the middle. So example here is moving an object with your arms. The effort is your upper arm muscles, so your biceps, triceps, and their accessory muscles. The resistance is the bones in your forearm, your hands, whatever object you are holding. The fulcrum is the joint between the ulna and the humerus. Let's look at illustrations to better imagine what's going on here. So with the first class lever, the fulcrum is in the middle. Second class lever, resistance is in the middle. And in a third class lever, the effort is in the middle. So nodding your head is an example of the movement with the first class lever. So the fulcrum is right there in the middle between the resistance and the effort. The second class lever has the resistance in the middle, so the weight of your body, as shown here by the load of the wheelbarrow. The fulcrum is the joint there, that's the wheel, and in your body it's your tippy toes. So the joint between your digits and your metatarsals. And then the effort is going to be your calf muscles. Third class levers are the most common type. The effort's in the middle. And so here's the effort. So if you kind of turn your head sideways, you can see that the biceps is indeed in the middle there. And of course I said biceps and triceps because they're all working together, but that's the effort there. That's the main one. Biceps is the big boy here. And so the resistance is going to be the bone and the flesh of your forearm and your hand and whatever you're holding. And then the fulcrum is your elbow joint. This is also called a speed lever. Another good illustration that would be here is someone holding a shovel. So you can't really lift a whole lot of weight with the third class lever, but you can move it quickly and over a long distance. The last section of this lecture will discuss the anatomy of selected synovial joints and then some diseases. All joints in the body are important. There are a few that have more clinical importance due to their movements of focal areas and the severity of injury if they are impaired. So let's look at a few of those. The first one is the Temporomandibular Joint, or TMJ. This is the biaxial joint of the lower jaw. It allows the hinge movement of depression and elevation, and also allows the gliding movements of side to side, and then your protraction and retraction. It often dislocates anteriorly. So with the mammals being able to move our jaw so freely to chew, it can cause the jaw to dislocate. So individuals who suffer from TMJ have a condition where the joint frequently dislocates. This can cause pain in the mandibles and the masseter and the temporalis around the temporal bone. It can actually cause tinnitus. It can cause teeth pain. It's pretty crappy to have TMJ. This is the temporomandibular joint, just showing you the extrinsic ligaments here, as well as the interior of the joint. There's an articular disc here and some cavities and all the good things. So the way that the mandible is positioned is it has this condyle or wheel that fits into a fossa or depression in the temporal bone. And here is showing the gliding movement side to side, which is a unique mammalian feature to chew. The next joint is the glenohumeral joint, or the shoulder joint. This is a multi-axial joint. It is the ball and socket. It is the most freely movable joint of the body. Thus, the enhanced mobility is offset by a loss of stability. So shoulder dislocations are common. Primary support of the shoulder joint comes from the rotator cuff muscles. These include the supraspinatus, infraspinatus, teres minor, and subscapularis. I'll show you them in the next couple of slides and explain their names. Rotator cuff muscles are easily torn, and injuries are very common. This shows some of the extrinsic muscles and tendons of the shoulder joint, as well as the interior of the shoulder joint, seeing the cavity there and the articular cartilage. You see the bursa and all that good stuff. Here's a really good view of the extrinsic ligaments, as well as the articular capsule binding the humerus to the scapula. The bursa and tendon sheaths, as mentioned earlier. All right. The rotator cuff muscles, 3 of the 4, are named relative to their position around the scapula. So the supraspinatus is the muscle that is superior to the scapular spine. Infraspinatus is inferior. This is the posterior side of the scapula. On the anterior side is your subscapularis. This is going to be on the, beneath or the bottom, deep to the scapula, and it fits in this fossa or this depression in the scapula there. And then here's the teres minor. Oftentimes we call that the bra strap muscle because that's kind of where that sits, where your bra strap would go. So these are your rotator cuff muscles, and when they are subjected to overexertion, or if your arm gets kind of pulled laterally, behind you, then it can tear these muscles and they will need surgery to be repaired. All right, the elbow joint is the humeral ulnar joint. So there are a couple of joints in this region, but it's the flexion and extension of the elbow that is the role of the humeral ulnar joint. When you do pronation and supination, that's a different joint. So the humeral ulnar joint is the elbow joint, and it's uniaxial hinge joint that allows flexion and extension of the forearm. Articular surfaces are highly complementary, but ligaments and tendons may become damaged by excessive use or weight-bearing exercise. They call this tennis elbow. This illustration shows the articular surfaces of the humerus. Here we see the trochlea of the humerus, which is a wheel-like condyloid structure. And then the ulna has this notch in it called the trochlear notch that fits with the trochlea of the humerus. They're separated by the synovial cavity, filled with the synovial fluid, buffered by the articular cartilage, surrounded by the capsule. The membrane will secrete the synovial fluid, and then we will have our ligaments that are binding these bones together. This is the tendon of the biceps and the tendon of the triceps to help us flex and extend our elbow. Here we see the extrinsic ligaments in the elbow here, binding it together. So recall there's two joints in this region. The one between the ulna and the humerus is the elbow joint that allows for the flexion and extension. The radius and the humerus do other things. They do the pronation and supination. Then we have the coxal joint or hip joint. The acetabulum means vinegar cup, and it is a deep socket that is highly adapted for weight bearing. The hip joint is a multi-axial ball and socket joint. However, the range of motion is more limited than the shoulder joint. Motions include flexing and extending the thigh, as well as circumduction. This joint is prone to osteoporosis. The first joint for which a prosthesis was developed was the hip joint. A broken hip is actually a fracture of the neck of the femur. This shows the head of the femur fitting into the acetabulum. There's an intrinsic ligament here that will bind the head of the femur to the hip bone. And then we have our joint cavity and our articular cartilage, our synovial membrane and synovial fluid. And then we'd have the articular capsule. And then we can see the extrinsic ligaments. The knee joint is the largest, most complex joint in the body. It is composed of two separate joints, the tibiofemoral and the patellofemoral. The tibiofemoral is where the tibia and the femur meet, and this is what gives us the flexion and extension of our knee. And the patellofemoral is where the patella and the femur meet, and it gives us a little bit of gliding motion. Here are some important features of the knee joint. The fibular collateral ligament connects the femur to the fibula and prevents the knee from moving medially. The tibial collateral ligament connects the femur to the tibia and prevents the knee from moving laterally. This holds the knee in place in anatomic position. The medial and lateral meniscus are a pair of C-shaped fibrocartilage that support the condyles of the femur. They add stability to the knee joint. Then we have the anterior and posterior cruciate ligaments. The anterior cruciate ligament is abbreviated ACL and prevents the hyperextension of the knee. The posterior cruciate ligament, or PCL, prevents the hyperflexion of the knee. Knee injuries are common. A lateral blow can tear the tibial collateral ligament, the medial meniscus, and the anterior cruciate ligament. The ACL and the meniscus can also be torn when changing directions too quickly while running, or from an anterior blow to the knee that causes hyperextension. Arthroscopic surgery is a successful treatment. The patellar ligament is used to repair the ACL. Here finally we can see the patella and the tendon of the quadriceps connecting to the patella, and then this is the patellar ligament. This is lateral, the fibula is lateral, so this would be the fibular collateral ligament, helping to prevent the femur, the knee moving medially, so it's going to hold it taut so it doesn't bow inward medially. And then the tibial collateral ligament is going to help hold the knee taut so it doesn't bend laterally. And then we see the anterior cruciate ligament and then the posterior cruciate ligament. So they make kind of an X shape, which is what the cruciate means. The anterior cruciate ligament, if we remember, will prevent hyperextension of the knee. So the ACL prevents hyperextension of the knee, so it prevents the tibia from moving forward. And the posterior cruciate ligament prevents hyperflexion of the knee, so it prevents the femur or the tibia from moving backwards, so it holds the bones taut together. This is a lateral view of the lateral meniscus. You can see that it's a C-shaped cup, like a half moon. That's what meniscus means. Helps to make more of an articular surface on the tibia, which is otherwise pretty flat, and the femur can fit into the meniscus with more ease. Superior view of the meniscus. That C-shaped cartilage there, made of fibrocartilage, will help to resist compression and also, make the articular surface more inviting to the femur. This is the anterior cruciate ligament, so it originates from the anterior portion of the tibia here, prevents that anterior movement of the tibia as well. And then we have the posterior cruciate ligament, which arises from the posterior part of the tibia and prevents posterior movement of the knee. This is what happens if there's a lateral blow to the knee. Bam! And so what ends up occurring when you get hit on one side of your body, shock waves form and they go through the tissues, and a lot of times you have two areas of injury. So you're getting a nasty bruise here, right, from where the hockey puck hit you, but because of those shock waves you're going to get a injury that is on the opposite side of the body that's even more severe. And this happens a lot with head trauma too. If you get hit on one side of your head, your brain knocks into the bones on the other side of your head, and you can actually have bleeding. So what's happening here is the lateral blow has sent shockwaves through the knee, and we're tearing all kind of stuff. So the anterior cruciate ligament gets torn, the medial meniscus gets torn, and the tibial collateral ligament gets torn. It stretched it too much because of those shock waves there, whereas these are compressed a little bit more. So the fibular collateral ligament doesn't get torn, and neither does the lateral meniscus. But they will get early bruised, but this is nasty here. And then again, I said that anterior cruciate ligaments can be torn if you turn too quickly while running, because it can twist this and snap it. Okay. So injuries and illnesses of synovial joints. Oh, one more thing to say as we go in there. These are like soft tissue injuries, right? And oftentimes soft tissue injuries, particularly of ligaments, tendons, menisci, things like that, will take a lot longer to heal and have more deleterious effects further on down the line than if a bone was broken. Because remember, bones are super metabolic, and they're constantly growing and regenerating, and there's a lot of blood flow. That's not the case here with soft tissue. There's literally no blood flow to these areas, little to none. Thus, these tissues are not going to repair themselves. That's why surgery is necessary. Surgery is necessary for broken bone too, but remember I taught you that a broken bone will mend itself even if surgery isn't done. It will just mend itself in weird ways. Unless, of course, it's a compact. I mean, there's a million unlesses. Sticking out of your leg or whatever, you're just going to die. All right, here's injuries and illnesses of the synovial joints. Joint injuries. All right, like I said, those soft tissue injuries, cartilage tears, sprains, dislocations. Bad news. Here's a torn meniscus here. And so it typically occurs when the meniscus is subjected to compression and shear stress at the same time. Sprains occur when the ligaments are stretched or torn beyond 6%. So the ligaments can only stretch about 6% of their length before they start to become sprained. And a dislocation is when the bones are forced out of alignment. Here is a shoulder dislocation. So you pop them back into place, but what happens when you've dislocated a joint like that is it has stretched the ligaments and tendons in there. And so then the dislocations tend to become, you're more at risk for them. Arthritis means inflammation of a joint. There are over 100 different types of arthritis. Examples include bursitis, which is inflammation of the bursa, and tendonitis was an inflammation of the tendons. Other examples of arthritis include osteoarthritis, which is the inflammation of the synovial joints from wear and tear and aging. It's the most common type of arthritis. It's very painful, and the articular cartilage is degrading. So there's a lot of heat, redness, swelling, and pain. And the bones are actually going to stiffen up and grind together during movement. Rheumatoid arthritis is an inflammation of the synovial joints due to an autoimmune disease. This one is hereditary, and the joints will eventually fuse together. This illustration shows the healthy joint with a nice articular cartilage here, good synovial cavity, versus osteoarthritis. The articular cartilage has been degraded, the synovial cavity is collapsed, and then rheumatoid arthritis has the swelling around it and inflammation, filling with blood, and the bones will fuse together. This is showing osteoarthritis, again, a healthy knee joint, and then we see hypertrophy and spurring of bone and erosion of cartilage. And in the rheumatoid arthritis, here we see the late stage, and the bones fuse together and cause the digits and other areas to look deformed as the bones are fusing together. Gouty arthritis occurs when high uric acid levels in the blood form needle-like crystals that settle into joints. This is usually caused by diet and the inability to expel excess proteinaceous wastes. Lyme disease is caused by a bacterial transmission from a tick, and the arthritis occurs if the bacterial infection is left untreated, and it can spread systemically. So if you see this bullseye's rash, or you're worried after getting bit by a tick, go get tested for Lyme disease. And then we have the gingerbread man. The doctor is saying, "Sore knee, huh? Have you tried icing it?" Ha ha